Two glass plates separated by a foil. Two flat plates of glass with parallel faces are on a table, one plate on the other. Each plate is 11 centimeters long and has a refractive index of 1.55. A very thin sheet of metal foil is inserted under the end of the upper plate to raise it slightly at that end. When you view the glass plates from above with the reflected white light, you observe that at 1.15 millimeters from the line where the sheets are in contact, the violet light of wavelength 400 nanometers is enhanced in this reflected light, but no visible light is enhanced closer to the line of contact. Part A. How far from the line of contact will green light of wavelength 550 nanometers and orange light of wavelength 600 nanometers first be enhanced? Part B. How far from the line of contact will the violet, green and orange light again be enhanced in the reflected light? Part C. How thick is the metal foil holding the ends of the plates apart? So here is the situation. We have two parallel plates separated by a thin metal foil, as you can see here. So we have basically light with a white light, but we're basically concentrating on the violet portion at the beginning. So we have a wavelength of 400 nanometers. That is basically what we're considering for the beginning of the problem. The index of refraction of the material is 1.55, so n is equal to 1.55, and at a distance x, which is 1.15 millimeters from the point of contact, we have the first enhancement in the violet. So x is equal to 1.15 millimeters. So if we look at different portions of light here, we have the first ray, number 1, is the incident light in air. So we have light incident on the upper plate, and 1 prime, what do I call 1 prime? The portion of the light that gets refracted in the upper plate. So basically 1 prime is the ray 1 that is refracted in the top plate. So I have labeled that T. So in the top plate with index of refraction N. So that's basically this portion here. And then we will have 1 double prime. That's the one that is transmitted into the air, into the thin metal foil in between. So because we have inserted this thin metal foil here, so we have 1 double prime, that is 1 prime refracted in the foil, and then we have number 2, that is basically one that gets reflected in air. So ray number 2 is 1 reflected in air. Then we have number 3, that is basically 1 prime reflected in the bottom of the top plate. So ray number 3 is 1 prime that's inside the top plate that is reflected from the bottom surface of the top plate. And then we have 3 prime, which is number 3 that gets refracted in air. 3 prime is ray number 3 refracted in air. And we have number 4, ray number 4, that is the one that is reflected in the metal sheet, at the bottom of the metal sheet here. So that is 1 double prime reflected in the tin sheet. 4 prime is ray number 4 that gets refracted in the top plate. So 4 refracted in the top plate. And 4 double prime is basically 4 prime refracted in air. So what are the candidates for interference at the top surface? Well, we have 2 and number 3 prime. So these can form an interference pattern. And then we have 3 prime and 4 double prime. So basically these two can form. So they're originating from the tin metal sheet. So let's list the candidates. So if you look at the candidates for interference at the top surface, we have ray number 2 and 3 prime, 3 prime and 4 double prime. Now, which one will work? We have a very thin metal sheet. The thickness of the metal sheet is much less than the thickness of these metal plates, D. So T is much less than D. So if we look at the offset between 2 and 3 prime, the offset in the rays, this is going to be too large and there will be no interference observed. So even though we have close to normal incidence light here, because the path traveled by 1 prime and 3 is way too long compared to the path traveled in this metal sheet, the offset between these two rays when they reach the top surface will be too high, so they won't be at the same point in space, so we won't have interference. On the other hand, if we consider 3 prime and 4 double prime, because they are originating from the reflection on the top of the metal sheet and at the bottom of the metal sheet here, there's only going to be a small path difference between these two, and they're traveling the same path within this top plate, so they're going to form an interference pattern. So basically we decide on which rays will form the interference pattern based on the thickness of the media they're traveling in. So basically 1 prime and 3 form a path difference in the top plate, but because the thickness of the top plate is much greater than the thickness of the metal sheet here, there will be a large offset. But on the other hand, for these two rays, for 3 prime and 4 double prime, which form a path difference within the metal sheet, since the metal sheet is very, very thin, this is going to basically form almost no offset at the top surface. So basically we will decide that they will form the interference pattern. So with this argument, we will only consider 3 prime and 4 double prime. That means we're considering the reflection from the thin sheet top surface and bottom surface. Okay, so let's start with part A. How much is the path difference between 3 prime and 4 double prime? Delta path difference between 3 prime and 4 double prime. So because they're traveling, these are close to normal incidence here. They're almost, we can consider them almost traveling top down and down up. So basically this is going to be h travels twice, so we will have a path difference of 2h. So this is basically 3 prime that is reflected from the top surface, and then we have an additional distance h down, h up before this ray forms, so we will have 2h path difference. So the path difference is 2h. And if I look at this geometry here, this distance is x and this angle is theta. So you can see that tangent theta is h divided by x. So what I'm calling h is x tangent theta. So therefore this is going to be 2x tangent theta. So 2x tangent theta is the path difference that forms in this material, which is 2x times, what is tangent theta? The thickness of the metal sheet divided by the length here. So it's going to be 2xt divided by L. So that's the path difference. And now, since 1 double prime to 4 reflection that's occurring at this interface here is going to be from the metal foil towards the so this is our metal foil that got inserted here. So this region is basically air, right? So we have to consider this region is air, and this is our foil that has been inserted. So that's not inside the foil, that's in air. So we will see that because we're going from a low index to high index here, a high index medium here, just like in Lloyd's mirror, there will be a path difference forming between these two rays as well. So we have to consider that path difference. This is reflection from higher index. Therefore, we will have an additional phase difference of pi forming. Okay, so we have two things happening at the same time. This ray, the path followed by this ray is basically 1, 1 prime, 3, 3 prime. And now the path followed by 4 double prime is 1, 1 prime, 1 double prime, 4, 4 prime, 4 double prime. Where is the extra path difference occurring? Here within the air gap that is formed by inserting this metal foil on one end. And we can see that that is forming an interference pattern for violet light at a distance x from the line of contact here. so at the point of contact, so we can see that h divided by x is tangent theta, so 2h is the path difference, approximate path difference, that's going to be 2x tangent theta, plus we have the reflection from low index to high index interface, so we have a phase difference of pi forming at the same time. So we can write the condition for constructive interference. So the condition for constructive interference is the path difference 2xt divided by L must be equal to m plus 1/2 lambda. This is condition for constructive interference. If we didn't have this pi phase difference, it would be m lambda. But because we have this pi phase difference, this is m plus 1/2 lambda. So m equals to 0 gives us our first constructive interference condition, and that corresponds to x is equal to lambda L divided by 4t. Now, do I need to modify this lambda? No, because this path difference is occurring in air, in the medium is air. I don't have to modify the wavelength. If the path difference occurred inside the material with index of refraction n, then I would have to make it lambda over n in that case. So then I find for another constructive interference criterion x prime for a different wavelength, this would be lambda prime L over 4t, which is lambda prime over lambda times x. So another constructive interference condition for a different wavelength is lambda double prime over lambda times x. So I can see that the constructive interference will occur for the 550 nanometers at a point 1.15 millimeters times 550 nanometers divided by 400, and as for the orange light, it would occur at x double prime 1.15 times 600 over 400. Okay, so we can see that x prime, the position where the green light forms the first constructive interference, is 1.58 millimeters, and for the green light we would have x double prime is equal to 1.72 millimeters. All right, so we have 600 divided by 400 times 1.15. That's the position of the green light first constructive interference, first enhancement. Now in part B, here again we have the condition for second constructive interference. So here I have redrawn the situation just to make it clear. So we have this, this is where we had the first constructive interference. Now we're looking for the second constructive interference at a greater distance from the point of contact. And now for the second constructive interference, we have m equals 1. So m equals 1 means the path difference 2xt over L. So that was our path difference that we have calculated. 2xt over L will be equal to 3 over 2 lambda. And this is occurring in air. So once again, this is air. This has been lifted by the metal sheet here. So we will find, this is for the second constructive interference, so let's call this x2. x2 will be equal to 3 lambda L over 4t. So we will see that x1 was at lambda L over 4t, so it will be 3 times x. So this is going to be 3 times x. This is 3 times 1.15, which gives us x2 of 3.45 millimeters. So that's for the violet. Now for the green, we have x2 prime. It will be equal to 3 times x prime now. So this will be 3 times 1.58, which will give us a location 4.74 millimeters. That's for the green light. And for the orange, x2 double prime, we have 3x double prime. That is 3 times 1.72. This will give us a location 5.16 millimeters. And now part C asks me the thickness of the metal plate. From part A, I know that the thickness is lambda L divided by 4x. So that's what I called x here. X was equal to lambda L over 4t, so t is equal to lambda L over 4x. So I can just substitute for the 400 nanometer light, that's the violet, 410 to minus 9 meters. The length is 11 centimeters, 11 10 to minus 2 meters, divided by 4 times 1.15 millimeters, 10 to minus 3. This gives me a thickness of 9.57 micrometers. Okay. And let's take a look at what we have done here. We have two glass plates separated by a foil. They are put on top of each other with parallel faces, and a thin sheet of metal foil is inserted under the end of the upper plate, to raise it slightly at that end. So when you raise it slightly at that end by inserting this foil, we form an air gap between these two plates. So when you view down from above with reflected white light, you observe at 1.15 millimeters from the line where the sheets are in contact, the violet light is enhanced. And we want to know for green light and orange light where the first enhancement will be, where the second enhancement will be in part B, and the thickness of the metal foil. Now, if we follow the light rays, the path of the light here, we see that if you compare the light reflected from the top of this plate and the light reflected from the bottom of this top plate, the path difference is occurring inside the top plate, but because the thickness of this is way too large compared to the thickness of the air gap here, there will be an appreciable offset in the beam. So if you want to see this, so if this is a very large thickness compared to this thickness, the point where the incident light hits the plate and the point where the reflected light from the bottom surface of the top plate hits the top surface, they're going to be really separated. Okay, so we will have this separation, large separation. even though we have close to normal incidence here, so we don't consider rays 1 and 3 primes constructive interference. Instead, we consider 3 prime and 4 double prime, because if you consider 3 and 4 double prime, the path difference is occurring within this thin metal sheet, and the offset between the two, because they're not forming the path difference in the top plate, is going to be very small compared to these two rays. So that's why we have to consider reflection from the top of the air air gap, top of the air gap and bottom of the air gap for this problem. It's the same story here if you consider the rays in the bottom plate, because they're traveling too much of a distance in the bottom plate, and there will be too much offset for the rays considered in that case. Therefore, we concentrate on rays 3 prime and 4 double prime. Okay. What is the path difference between these two rays? The path difference is occurring in the air gap when we have the motion of the ray coming down and the ray going up. So we have 3 prime, basically, that is reflected from the surface, and then we have 4 double prime, which travels this extra distance h plus h, 2h, in order to reach the top surface. So the path difference is 2h, which from this geometry is tangent theta is equal to h divided by x. So it's going to be 2x tangent theta, and tangent theta is also the thickness of the metal foil divided by the length of the plates. So it's 2xt over L. And now I'm also careful, because in addition to this path difference, I have this ray hitting an interface between air and material with index of refraction n greater than 1. So this n is greater than 1. There will be a phase difference developing of pi at this interface, which makes the condition for constructive interference 2xt over L equals m lambda becoming m plus 1 half lambda because of this additional phase shift. Okay, so m equals 0 corresponds to first constructive interference. X is equal to, m equals 0 gives me x is equal to lambda L over 2 times 2, 40. And for different wavelengths, we will have lambda prime, x prime, lambda double prime, x double prime. So basically, we have to scale x with lambda prime over lambda to find where the constructive interference for other colors occur. So that's what we have done here. 550 divided by 400 for green, and 600 over 400 is the scaling factor for orange. This gives us the place of the first constructive interference for green and orange. For second constructive interference, we change the condition. M equals 0 becomes m equals 1, 3 over 2 lambda. So this gives us, instead of lambda L over 40, 3 lambda L over 40. And therefore, the places of the second constructive interference for different colors will be just 3x, 3x prime, and 3x double prime. So that's what we have done in part B. And in part C, we can calculate the thickness of the foil T here by looking at the result from part A. T is equal to lambda L over 4x. Substituting the numbers, we find the thickness to be 9.57 micrometers.